So what we're going to be looking at today explains the construction of an 11 kV overhead transmission lines with wooden poles to include but not limited to. We're also going to be looking at pin insulators, loops and bowls. We're going to explain the skin effects that apply to OHL conductors and explain the problems that are caused by inflammation and how this is minimised. We're going to look at surges and how they can occur in overhead lines and explain two different methods of surge control. So we've just got a different variety of wooden poles here. Overhead transmission lines require some support to carry the conductors. The supporting structures for overhead transmission lines conductors are various types of poles and towers called line supports or electrical poles. Properties of these lines supports. Line supports should have high mechanical strength to withstand weight of conductors and wind loads, etc. Light in weight without the loss of mechanical strength. Poles should be cheaper in cost and eco-friendly. High lifetime because frequent replacement of poles is uneconomical. They should be easily accessible with conductors for maintenance. So we're just going to have a look at the various different types of poles then now. Look at is wooden poles. Wooden poles are made of wood obviously and are suitable for short runs, maximum distance of up to 50 metres. Wooden pole supports are cheap in cost, easily available, provide natural insulation properties, and they're a lot more economical. The wooden poles generally tend to rot below the ground level, causing foundation failure. In order to prevent this, the portion of the pole below the ground level is impregnated with preservative compounds like creosote oil. But nowadays, these poles are out of use. They're replaced by RCC poles because of their longer life. Disadvantages of wooden supports: they have a tendency to rot below the ground level, comparatively smaller lifespan of only 20 to 25 years. They can't be used for voltages higher than 20 kV. They've got less mechanical strength and they require a lot more periodic inspection in comparison to other types of poles. The next ones we'll be looking at is steel poles. The steel poles are used as a replacement for wooden poles because steel poles possess greater mechanical strength. Longer life than wooden poles, they're able to withstand longer lifespans. These poles are generally used for distribution purposes in the city. This type of support needs to be galvanised or painted. They do this in order to prolong their life. There are three different types of these poles. The first one is rail poles. There's also tubular poles, and the final one, rolled steel joints. The next type of poles we'll be talking at is RCC poles. This stands for reinforced concrete. These poles have become very popular in recent years. They have greater mechanical strength and a lot longer lifespan. They permit longer spans than steel poles due to the mechanical strength. They also look a lot better than many of the wooden and metal ones. They require very little maintenance and have good insulating properties. A couple of the drawbacks of these: they're very heavy in weight and the manufacturing costs are very expensive, but they're a good alternative for all types of line supports. The final one we'll look at, but it's not really covered by the scope of our assignment brief, is steel towers. In practice, wooden, steel and reinforced concrete poles are used for distribution purposes at low voltage of up to 11 kV. To transmit higher voltages than 11 kV, we use steel towers. Steel towers have greater mechanical strength and longer lifespan. They can withstand most severe climate conditions and permit the use of longer lifespans, and we can increase or decrease the length of the pole by assembling some or more arms. They are more cost effective but require more space to establish. The final part I'll be looking at is the pin insulators. As the name suggests, the pin insulator types is secured to the cross arm of the pole. There is a groove on the upper end of the insulator for housing the conductor. The conductor passes through the groove and is bound by the annealed wire of the same material as the conductor. Pin insulators are used for the transmission and distribution of electrical power at voltages of up to 11 kV. Beyond this operating voltage, the pin insulator types become too bulky and hence uneconomical.
I'm going to be talking about loops and bows. For straight through power lines, each side of the pole is needed to be connected to each other. This is done with the use of loops. The loop is simply a connection that is looped over the top of the wooden pole and is insulated at the top via the pin insulator, and then onto the next section of the power line. Some lines need to go in another direction, and loops help this with their flexibility. In this scenario, as shown in the picture, bows. In order to connect the cables running up the structure of the pole and also from the transformer, a connection is made with the use of a series of cables off of each line section. These line sections are called bows. Bows are used in many different types of overhead transmission applications, where they are also connected via cables running up the structure to where they are terminated, and the bows are what makes the connection between the termination point and onto the section line sections. On some designs, such as ABSD, air brake switching device systems, which is where the supply from one side of the pole is connected to bows onto a switch type mechanism, so these lines can be isolated, which is done by using a long insulated handle which reaches down to floor level, which can open in order to break the circuit.
I'll be talking about the skin effect. The skin effect is the tendency of AC current to become distributed within a conductor as the current density is larger near the surface of the conductor and decreases nearer to the centre. This leaves the core deprived of necessary number of electrons. There can be some cases where no current flows through the core at all. The electric current flows mainly at the skin of the conductor between the outer surface and a level called the skin depth. The skin effect causes the effective resistance of the conductor to increase at higher frequencies. Where the skin depth is smaller, this reduces the cross section of the conductor. The skin effect happens because of the opposing eddy currents induced by the changing magnetic field from the AC current. The three wire bundles in this power transmission installation act as a single conductor. A single wire using the same amount of metal per kilometre would have higher losses due to the skin effect. When transmitting alternating current, bundle conductors can be used to avoid the reduction in ampage of a single large conductor due to the skin effect shown by the photo on the left. You can reduce the skin effect losses in transmission lines by properly laminating the conductors and adjusting the velocity of transmission of the waves. The photo on the right shows the conductor where the skin effect takes place around the outer surface.
The last part of the assignment question, we're going to talk about power surges and how they occur in overhead lines. Power surges are spikes in voltages which happen very briefly. Power surges can vary in duration and magnitude. Power surges in overhead lines can be caused from both external and internal factors. Examples of external factors which cause surges are electrical storms / lightning strikes, trees making contact and damaging the overhead lines, or power surge can cause when restored from an outage. Internal factors are as follows: earth faults, sudden change in loads on the system. One method to control surges are surge arresters. Surge arresters protects power systems from damages caused by lightning. They do not absorb or prevent the lightning. It diverts the high voltage current to ground and limits voltage produced by the lightning. It protects equipment in parallel with it. The main component of a arrestor is a metal oxide resistor. Normal conditions, the mauve is an insulator. Under fault conditions, the mauve becomes a conductor. Another control method is a shield wire. The shield wire above the pylon shields the lines as it intercepts the lightning strikes before they hit the current carrying conductors below, also known as a ground wire or earth wire. They are located at the top of transmission towers. They are bare conductors and effective just a low resistance path to earth. They are connected to ground at each tower in the distribution system. So simply put, shield wires save the transmission lines from the impact of lightning strikes as it is placed above the phase conductors.